then we know from the here this a square u naught, which is equal to a cube u naught. So when you can see that there is a pattern here, right? So uk is equal to a to the power k u naught. And I will write that also here. uk is equal to a to the power k u naught. So if you find uk, then we will know the kth element in the Fibonacci series, right? So I don't know whether we simplified the problem or complicated it here, because now we have to find the kth power of this matrix, right? So if you just think of multiplying that matrix that many times, let's say if you want to get the 100th element of the Fibonacci series, basically what that means is we got to get a to the power 100 of the matrix. So basically we have to multiply that matrix 100 times, so which is operationally very costly. So we cannot, I mean, we can technically do it, but it is going to take a lot of time. So we have to find a better way to find the u to the power k, right? So to do that, what I can do is I can basically write this matrix in a diagonalized form. So it's called matrix diagonalization. So A can be written as AS delta S to the power, S inverse. So this is called diagonalization. Again, there are a lot of theory available to identify when the matrix can be diagonalized and things like that. So I'm not going to go into the details, but this matrix can be diagonalized. But this S is eigenvector. This S is an eigenvector. This is the S inverse. Again, obviously it's a eigenvector inverse, and this lambda is the eigenvalue. So eigenvalue. So first, so I'm saying eigenvector, eigenvalue. So I have to tell what is eigenvalue and eigenvector, right? So A minus lambda I. So you can take a determinant of that and equate that to 0. Then it will create a characteristic polynomial. So if you solve the characteristic polynomial for lambda, then that lambda is the eigenvalue of the matrix A. So I repeat one more time. So if you equate A minus lambda I determinant to 0, and that is a characteristic polynomial, and if you solve the characteristic polynomial for lambda, then that lambda is the eigenvalue of the matrix A. To get the eigenvector, so A minus lambda I x equal to 0. So in other words, if you take null space of the matrix A minus lambda I, not the determinant, the matrix A minus lambda I, then the null space is the eigenvector of the eigenvalue lambda. So again, this eigenvector and eigenvalue has a lot of applications. Even the Google web server, not Google web server, Google search engine is the algorithm, page rank algorithm is based upon this eigenvalue and eigenvector. So this has a lot of practical applications. But again, I just want to focus on this. Maybe future lecture, maybe I can focus on the application of eigenvalue and eigenvectors. So this is the x is the eigenvector, and if you solve for lambda, then that is the eigenvalue. So this is lambda is eigenvalue, and this x is eigenvector. Okay. So let's get this eigenvalue now. So we know A. So A minus lambda, which is, and we gotta get a determinant of it. 1 minus lambda, 1 minus lambda. Determinant, again you will get x1 minus x2, this cross product of it, but anyway we are going to equal to 0, so it doesn't really matter, so I'm not going to worry about that. So if I equate this to 0, then it becomes say minus lambda 1 minus lambda into 1 minus lambda minus 1 equal to 0, which means lambda square minus lambda minus 1 equal to 0. So this is the characteristic polynomial of this matrix A, and if you solve this polynomial, then you will get lambda, which is the eigenvalue. So let's go back to the quadratic equation. It's a quadratic equation. So what lambda is equal to minus b plus or minus square root of b square minus 4ac by 2a, which is equal to 1 plus or minus square root of 5 by 2. So the lambda is 1 plus or minus square root of 5 by 2. So I will store that also here. So lambda is equal to 1 plus or minus square root of 5 by 2. So that is the eigenvalue of the matrix A. So now I'm going to get the eigenvector, right? So let me write down A minus lambda I, which is 1 minus lambda 1 minus lambda. So this is A minus lambda I. Again, I is the identity matrix, right? So I'm gonna multiply x1 x2 equal to 0. So if you think about it, this is a null space of this matrix A minus lambda I. So what that means is we had to find x1 and x2, a vector which is orthogonal to this matrix. So when we find this x1 and x2 which is orthogonal, then it means the dot product of this two matrices is going to be 0 because they are going to be perpendicular to each other. So now we have to find x1 and x2 here. Again, we can use the Gaussian elimination to find x1 and x2. Right, it is a very simple Gaussian elimination. So first we gotta get rid of this, right? So so you have to multiply by something and do an addition to this row so that this will get a 0. So what I'm saying is multiplied by x plus 1 is equal to 0. So we have to find what is x. So 1 minus lambda x equal to minus 1, x is equal to minus 1 minus 1 divided by 1 minus lambda. So if you multiply that, so this element is going to be 0. So here what is going to happen is, so you want to do the same thing, minus 1 minus lambda, then you add this here, right?